All right, in this video, we're just going to be practicing double integrals. I'm just going to work a few examples and, just to give you, a very concrete picture of what this computation process looks like. So what I'm going to do is I'm going to just grab some random double integrals from the textbook. Like I'm going to start with, okay, I'm sitting here in the Larson textbook, I think one of the newer editions, this is 14.1.11. So it's the integral from 0 to 1, 0 to 2, x plus y. Okay. And so how are we going to do this? We're going to use parentheses. That's like the big thing here. We're going to practice, we're going to do partial antidifferentiation, and we are going to, but we're going to start from the inside and we're going to work our way out. So what I'm going to do is I'm going to block off this integral in parentheses, okay? And I'm going to do that, kind of inside the parentheses. So if I want to take an antiderivative of x plus y with respect to y, just like when I took the partial derivative, I'm going to pretend that anything that's not y is a number, like 10 or 2 or something. So if I had the antiderivative of 10 plus y dy, I'd have 10y plus 1/2 y squared. And that's exactly what I'm going to do. So I'm going to say x times y plus 1/2 y squared. And then we remember what we do after we figure out an antiderivative. We plug in the top and bottom and we subtract. Okay, now at this point, I need to remind you that because we're integrating with respect to y, these are y values. This is running from y equals 0 up to y equals 2. Okay, and this is still going to get integrated from 0 to 1 with respect to x. All right, so what I'm going to do is I'm going to plug in top and bottom and subtract. So I'm going to say that's 2y plus 1/2 of 4 squared is 2. And then I can see when I plug in y equals 0, I'm going to get 0, so I'm going to just be happy with that. This is now the integral from 0 to 1 of 2y plus 2, wait, pardon me, 2x plus 2, right? Y was 2, so I've got 2x. dx as x runs from 0 to 1. This is the type of thing that, you could use Math 9 on the TI-84 to do this, or you could save the time that you would spend going and finding that thing and typing and just do it, right? This is going to be x squared plus 2x from 0 to 1. So from x equals 0 to x equals 1. So that's 1 plus 2 is 3 minus 0 is 3. Okay, and then I'm happy, right? That's me computing a double integral. You know how to compute a double integral. Okay, maybe I'll just look at one that looks a little more challenging. Oh, yeah, maybe you'll like this. Here's another one. This is 14.1.19 from the Larson book. And I'm going to say that 19 is 0 to 1, 0 to x. Of the square root of 1 minus x squared dy dx. All right. And so I'm going to, one thing I'm going to point out on this is this is the type of thing that was hopeless when it came to single variable calculus, right? We couldn't integrate it, right? There just is no antiderivative. Actually, hold on, that might be a lie. I think this one's trig substitutable. Yeah, I'm pretty sure it is. But we don't do trig substitution in AP Calculus, so I'm not super fluent on it. But again, we're just this is going to be something that we can really work with. Okay. And what I'm going to do is, okay, this whole thing has nothing to do with y, so its antiderivative with respect to y would be the same as the antiderivative of 5 with respect to y. It would be 5y. So it's going to be this thing multiplied by y. Okay, so this is going to be the integral from 0 to 1 of y times the square root of 1 minus x squared as y runs from 0 to x, right? Because if it's dy, this is a y value and that's a y value. Now when I actually plug in y equals x and y equals 0, I'm going to have the integral from 0 to 1 of x times the square root of 1 minus x squared dx. Okay. This is a u substitution situation, right? Because the derivative of 1 minus x squared is proportional to x. Okay, so what I'm going to do is I'm going to let u equal 1 minus x squared. So, yep. Okay, so this is equal to the integral from 1 to 0 of the square root of u and then negative 1/2 du, right? Okay. You know, if you need to sit and write out, you know, make a box, if you're a U-box type of person, or if you want to, you know, write it out like I used to in the AP class, that's fine. But I'm going to just generally kind of pass in change of variables without much fanfare in this class. So this is the, you know, the nice type of thing that we can definitely do. This is going to be 2/3 u to the 3/2. So it's going to be 2/3. So negative 1/2 of negative 2/3 because it was backwards. And, well, that's 1/3. Okay. All right, I think I'll do one more example for this video, maybe see if I can find something that's really weird. Let's see. Oh, yeah. All right. Oh, yeah. I heard a question in the crowd. Like, the reason the bound switched was because when u is 1 minus x squared, that becomes 1, that becomes 0. I'm just looking for the perfect problem. I'm being too picky. But, oh, I know, I found just the one. Something I'd kind of forgotten about, but I know that, you know, some of y'all might need the practice on, would be, you know, an improper integral. So let's look at, that's not going to work. I know that one's going to diverge. How about one that I'm not sure of, but I suspect has got to diverge, right? It's going to be integral from 1 to infinity of the integral from 1 to infinity of 1 over xy dy dx. Okay? So, or maybe, you know, this thing's got so much symmetry to it, maybe I'll integrate it dx dy, right? I think both of them I've integrated with respect to y first, and that is not, you know, always going to be the case. So I'll say dx, then dy. All right, and what I'm going to do is I'm going to go over here, and I'm going to find an antiderivative of this thing with respect to x, and so it'll be log absolute value of x. I do have that 1 over y, so I'm going to have to account for that. So it'll be 1 over y times the log of the absolute value of x as x runs from 1 to, as x runs towards infinity. So, and then this is something that we're going to want to take the limit of as b goes to infinity. And then I'm going to integrate that from 1 to infinity with respect to y. But you can see that this limit isn't going to exist. Okay? This limit is problematic because I'm trying to take the limit of the log of b as b goes to infinity. Okay? And you think, you know, what kind of exponent do I have to put on e to get a really large number? And you're going to have to put a really large exponent on it. Okay, so this one diverges because of the interior integral not happening. And I think that shouldn't be too surprising. We know that the improper integral from 1 to infinity of 1 over x dx diverges, so, you know, wouldn't be surprised that this one does too. To be honest, I was kind of hoping for an improper integral that converged, but I saw that one and I was like, well, at least I know what's going to happen with that one when I run it. So I'll put some improper integrals on your practice, some ones that are going to require UDU substitution, maybe one that requires UDV, just to get your practice going. But this is just a couple of examples on actually computing double integrals.